This presentation is entitled An Architecture to Deliver the Holy Grail of IT. Now, the Holy Grail of IT, I claim, is the ability to provide Google-like queryability across something called structured data. And not only to query across it, the ability to compute on it. In this presentation, we talk about the architectural components needed to support this most ambitious goal of delivering the Holy Grail. An architecture to deliver the Holy Grail of IT. So, what is meant by the Holy Grail of IT? What is the definition? It's the following. First of all, it's the ability to provide Google-like query capability on structured data. Secondly, it's the ability to compute on any structured data within and across enterprise systems. Now, when you look at search engines like Google, they have the ability to query. What they do not have the ability to do is to actually perform computation. So this second definition here is an extension of what search engines like Google can do today. In order to deliver the Holy Grail, a number of information technology challenges must first be met. First of all, there is the notion of accessibility. It turns out much data today is still in paper form. A second challenge, disparity. Information today oftentimes resides in what are called silos. A third challenge, computability. Much data today is still in an unstructured form. A fourth challenge, queryability. If you have structured data, the technology today is such that it is very difficult to navigate complex structures. Another challenge, one of fragility. Oftentimes in an enterprise system, whenever you make changes to one layer of the architecture, you oftentimes get this ripple effect where other layers break. Another challenge, one of rigidity. The inability to easily change data schemes on the fly. Another challenge, one of complexity. Oftentimes, enterprise systems today are comprised of potentially tens of thousands of underlying database tables. In order to query such data, you actually have to know the names of those potentially tens of thousands of tables. Another challenge is one of evolvability. Let's say you have a legacy system and you want to introduce a new system into your enterprise. The challenge is migrating the data from your complex legacy system to your new system. Another challenge is one of interoperability. Today, interoperability is restricted to standard message exchanges. And lastly, one of expressibility. The challenge today, in order to do queries on structured data, you have to have IT skills. Let's take a look at a set of architectural steps that solve the information systems challenges identified on the previous slide, and in doing so, deliver what I've identified as the Holy Grail of IT. First step is to create a simplified data warehouse schema, followed by mapping that enterprise data into that data warehouse, creating a knowledge layer using something called ontologies, and using that knowledge layer to categorize data in the warehouse, and using TCSQL capabilities to write a library of generalized SQL queries here. And then write a compiler that can map text strings into these underlying SQL queries in this library. And lastly, to create an application layer to distribute queries to appropriate servers and aggregate the results. In building this architecture, we're going to utilize a number of technologies. We're going to utilize information technologies, SQL and XML. We're going to utilize knowledge technologies, these things called ontologies. We're going to utilize something called natural language processing, which provides the ability to ontologically categorize structured data and unstructured data. And lastly, we're going to utilize a technology called TCSQL, which provides the notion of something called a soft schema and provides something known as transitive closure. This technology called TCSQL is a new kind of technology featuring the following capabilities. First of all, it features the ability to do graph management. In particular, the maintenance of this thing called transitive closure. It features the notion of something called soft schema, which provides the ability to support object-oriented programming directly in a relational database system, complete with notions of classes and objects and single and multiple inheritance and polymorphism, and a collection of other capabilities on top of these two basic capabilities. To begin, let's look at a database table you might find in an electronic healthcare record system for healthcare. So something that looks like the following: a column of names, a column of visit dates, and a column of diagnoses. Now, with such a table, this is a table you'd find in an information system. There are certain questions you might want to ask. You might want to ask, tell me all the patients here that have ulcerative colitis. So you can write a select statement that basically is looking in the fact column here for something called ulcerative colitis, right there. You might ask, anyone here have Crohn's disease? Again, you can write a select statement specifying where fact equal Crohn's disease. We see such a patient there. What if we wanted to ask, find all patients that have a digestive system disease? Well, you'll notice in our fact column here, there is no value that says digestive system diseases here. And so what you would have to do instead is write a select statement and then include a comma-separated list of things that constitute a digestive system disease, ulcerative colitis and Crohn's disease. What if I want to ask patients who have an autoimmune disease? Well, again, that ends up being a comma-separated list. I have no idea what that looks like. But the problem here is that in these higher level kinds of questions, in order to answer them, given simply an information system, I have to have a hard-coded list of legal values. Let's look at the difference between data versus information versus knowledge. If I showed you the following, would you consider this to be data or information or knowledge? Well, it turns out it's just data. And the reason why is because you look at this and it looks like a column of names. That's because it is something you recognize. This looks like a column of diseases. That's because you're familiar with it. But by itself, it is merely data, just text strings. Now, if I add column headers here, these column headers are what are known as metadata. And so what we get is data here plus metadata is our definition of information. Well, what if I take and put an overlay here, the following? We see type 1 and type 2 diabetes are specializations of this more general category of diabetes. Ulcerative colitis and Crohn's disease are specializations of this more general category called digestive diseases. So what do you call this structure here, this knowledge overlay? I call it meta-information. And so my definition of knowledge is information plus meta-information. This knowledge overlay here is something called an ontology here. There are semantic relationships between the nodes here. And what this allows you to do is the following. If you view this as a relational table here, you can certainly ask questions about who has type 1 diabetes in your database here. What an ontology overlay allows you to do is ask higher level questions. Tell me all the people in my system that have diabetes in general or have autoimmune diseases in general. So let's look at an example that further illustrates the difference between an information system and a knowledge system. So we're going to look at a healthcare example, the notion of diabetes mellitus. So in an information system, such as an electronic healthcare records system, you can ask queries that are specific with regard to diabetes mellitus. Tell me all patients in the hospital that have diabetes mellitus. When you take your information system and overlay it with a set of ontologies, you get a much richer set of questions you can ask it. So for example, with this notion of diabetes mellitus, we can return a set of medical devices associated with it, genes associated with it, body parts associated with it, diagnosis procedures, lab procedures, so on and so forth. You get the idea. The object-oriented paradigm can be represented as a graph problem. So here we have a class here called class 1, which has properties A, B, and C, and a has a relationship between the class definition and its associated properties. We also have another class here called class 1.1 with properties D and E. And we see a relationship here between these two nodes, an is-a relationship, meaning that class 1.1 is a specialization of class 1. Now let's look at a graph here. Let's look at what happens if we want to instantiate class 1.1. Let's look at the equivalent object graph. In this case, it would look like the following. Assuming we want to instantiate class 1.1 and we're going to call that object 1, what happens is the following. We first want to instantiate properties D and E, and then we want to look at this inheritance is a link here to inherit properties A, B, and C, which is what you see down here. Okay, now let's look at the relational tables needed to support this paradigm here. So we have the notion of a class table here, which represents the nodes of our class graph here. It's basically a name-value pair here, and we have a type column here, and legal type values. This represents basic class types here. We have a class connection table of parent-child nodes here, and a connection type here. In this case, it's going to be either has-a or is-a. And then we have a transitive closure table representing the transitive closure of this class graph. And assume for a minute that this transitive closure table is automatically populated and managed whenever nodes or connections are added or deleted in this class graph. Let's look at the tables needed to support our object graph here. We have a table called object, which represents the nodes of our object graph here. Again, it is basically a name-value pair with a class column here representing the kind of class that we're instantiating here, including the class properties. We also have an object connection table here, which represents the connections of our object graph. So it's a parent-child pair, again with connection type. And we have a transitive closure table associated with our object graph. And assume here also that this transitive closure table is maintained automatically whenever nodes or connections are added or deleted in our object graph here. So this whole paradigm here I'm describing here with these 6 relational database tables is something known as a soft schema. In the last slide, we looked at the notion of something called a soft schema and the 6 relational database tables associated with it. In this slide, we're going to look at a query which utilizes a soft schema and does a join to conventional relational tables like you see here. In this example, we're going to do the following query. Find all diabetes patients here. So at the top here, we have a graph, something called an ontology, where you have a semantic relationship between nodes here. In this case, it's an is-a relationship here. At the bottom, we have a standard relational table, an electronic healthcare record table here with patient information. And so the query looks like the following select statement here. And what we're going to do is we're going to play computer and run through step by step what happens in executing this query. In the first part here, we have a where transitive closure patient is diabetes. So we show that here. And what we're going to do is look at all of the children, in other words, all of the descendants in the transitive closure table here. So that shows up in purple here, all the descendants of diabetes. And then what we're going to do is a join on the electronic healthcare record table here, where the fact value corresponds to the descendant value here of the transitive closure. And then we're going to return here the select e.patient. We're going to return the patient column information here in the result here. Now this query is an example of a query type called a subsumption query. Let's look at an XML document example. In particular, we're going to look at an XML document pertaining to pharmaceutical. So here's our document here. And we have this code field here, this code tag, I should say. One of the things you can do with TCSQL is it provides an ability to import this data here into corresponding soft schema tables, object connection, and object transitive closure here. So in fact, the data in these tables I indicated earlier represents a graph here. So let's say you want to pull out all of the tags here in your XML document, the code tags. I can write a select statement here on the soft schema tables as follows. Select star from the object table where name equal code. Let's say I only want to pull out the code tags within the context of this dose administration parent here. I can write a select statement as follows here. Notice I'm using the transitive closure table here, basically saying starting from this node here, find all of the code attributes underneath here, and that's what this select statement represents. Let's look at another XML example. In this case, another XML document in the healthcare field here. So here's our XML document. Notice here we also have code information, but now the code information is an attribute of a tag called code here. So once again, as I mentioned in the last slide, TCSQL provides the ability to import this XML data into the soft schema tables here. And again, that represents a corresponding graph here. And if I wanted to pull the code information out, I can write a select statement as follows, querying from the soft schema tables here. And if I want to limit the code values to just the context of section here, I can write the following select statement. Again, it uses the transitive closure table to bound the context of the code attribute underneath the section field here. So now we've looked at two XML documents, both in the healthcare field here, both containing code information here. Now, let's say I would like to write a query that pulls code information from both of these documents here. Well, I could do the following, select star from object table, where name in, now I have a comma separated list of the names of the attributes in both documents here. Now, one of the problems with this approach is, well, if I have a third document or a fourth document in the healthcare field and their code attributes are called something else, I have to hard code this comma separated list with all the different names of those attributes in all the various kinds of documents. What I can do instead is the following. I can introduce a superclass here. I'll call it vocabulary code here. And I can create an is-a relationship here to all these different kinds of code attributes here and point it to this generalized vocabulary code. I can then write a query that looks like the following here. And notice what we're using here is the transitive closure for the class table here. And we're looking at this superclass called vocabulary code. The advantage of this now is if I add new XML documents here that have different attributes referring to code, I don't have to change this query. It's always correct. This is an example of something called a polymorphic query. Given two complex enterprise systems, as we see here, what's the most common way for these systems to talk to one another? Well, it's via message passing. It's typically something like an XML standard that is defined for an industry. Instead of message passing, we're going to propose an architecture which uses a soft schema. So here is our two complex enterprise systems. And imagine a star schema data warehouse in between the two and an ETL process that pulls data from these complex systems into this data warehouse. And imagine that being overlaid with a knowledge layer, a set of ontologies. And imagine being able to write SQL queries on top of this star schema data warehouse. So let's take a closer look at some details here. We have an ontology here, and we have three soft schema tables representing the information in our graph here. Imagine we have enterprise data, and what we want to do is import XML into a soft schema warehouse here. So now we have both our ontologies represented with a soft schema, and we have our enterprise data represented with a soft schema. So let's look at what a query might look like. Find all patients with an autoimmune disease. So it would look like the following select statement. We end up using a copy of the transitive closure to traverse this particular graph here, and we use another copy of the transitive closure to traverse our XML document. Okay, so let's go back to our architecture diagram again. What I've shown here is the number of tables representing our data warehouse and ontology is very, very small. So what we want to do at this point is to create a library of SQL queries that can traverse the structure here. And that enables us to do the following. We can write a compiler that takes a high-level query, something like a Google text string, and compile it into a collection of SQL queries. Let's look at a Holy Grail of IT example, something that would be very difficult to do with a search engine such as Google. Imagine you wish to determine how many people in Illinois have an autoimmune disease. Imagine you have a graphic such as the following that shows the United States broken down into regions, regions broken down into states, states broken down into counties, counties broken down into cities, and at the leaf nodes, the names of healthcare institutions. Imagine being able to do the following. Imagine being able to take your query and to drag and drop it into a box, and to have that query request propagated to all of the descendant nodes, and then being able to execute and aggregate the results together. Now this would be very difficult to do with a search engine such as Google for the following reason. In order to execute such a query, someone would have had to do that analysis in advance and then take that result and publish it in a text document. Only then would it be possible to execute such a query in a search engine such as Google. So let's summarize what we've learned here. Why is this valuable? First of all, I've demonstrated that the use of industry standard ontologies provides an effective way of categorizing enterprise data. Secondly, keep in mind that XML is ubiquitous. It's used throughout the entire software industry today. Third, I've demonstrated not only semantic interoperability, but computing interoperability.